Hello everyone. In this section, we consider the evolution of a protoplanetary disk, an accretion disk around the CTTS. Gas migrates toward the protostars. Energy is removed from a disk as heat, but the angular momentum is conserved. In the order of estimate, energy is expressed minus gm star over r. Capital M is a mass of a disk. Capital R is a radius of a disk. Then angular momentum is expressed mr times v. V is a rotational velocity of a disk. A disk will evolve to the configuration with the least energies, keeping the total angular momentum. In ideal situations, only a single molecule moving far away from a central star, except a single gas molecule, all the mass is migrating toward the central stars. So we'd like to consider how to transfer the angular momentum outward and transfer the majority of mass inward in an accretion disk. So basic assumption of a disk. We use 4 assumptions. First assumption is a thin disk. Second assumption is an axisymmetric disk. So there is no special directions in the disk. So if you consider some physical values, partial derivative of a physical value with respect to the angle of theta is gonna be 0. Third assumption is the disk mass is much smaller than the star mass. Fourth assumption is the rotational velocity is much larger than the radial velocities. Then, as I explained, we assume the thin disk. We'd like to simplify the problems. So we ignore the vertical structure of a disk. So we integrate over the vertical directions. Density is integrated over the vertical directions from the minus infinity to the infinities. We call the surface density, capital sigma. The unit of the surface density is a gram per square centimeters. The fluid velocity is estimated by the value at the midplane. G equals 0 corresponds to the midplanes. Then we'd like to consider the evolution of a protoplanetary disk. First equation is the equation of continuities. We express the equation of continuity in a cylindrical coordinate. We use some assumptions. Axisymmetric disk. So this term is gonna be 0. And then 2 terms from the second and third terms can be combined into the single terms. Then we'd like to integrate these equations from the minus infinity to the infinities in the z directions. Then we integrate. Then first term is expressed ln sigma ln t. And the second term is expressed, so v sub r is estimated by a value at the midplanes. We just integrate the rho with respect to z. The last term is expressed equal to the 0. Then this term becomes 0 because rho equals 0 at the z equal plus minus infinities. So third term is 0. Equation of continuity is expressed ln sigma ln t plus 1 over r round r. R v sub r sigma equals 0. This is the equation of continuities in two-dimensional motions. The equation of motions in the z coordinate. The right hand side is first term is a pressure gradient. And second term is a gravitational force from protostars. We like to consider the force balance. V sub z equals 0. Left hand side becomes 0. The equation becomes simplified. Sound velocity in the z direction is a constant value. C square equal round p round rho. Round p round z is modified. Round p round z equal round rho round z round p round rho. So this is correspond to c squares. C squared round rho round z. Then we need to solve this equation. This is a practice 3.1. Solve the following differential equations. integrate the both sides of the equations. Left hand side is expressed round log rho over round z. Then we'd like to integrate from the 0 to the z dz. Minus v sub k square over c square is a constant values. And then also r square is a constant values. Then we'd like to integrate z with respect to z, 0 to the z. Then you could perform this integrals log rho minus log rho sub 0. This is rho at z equals 0. Equal minus actually v square r square omega squares. Then omega sub k square over c square times 1 over 2 g squares. So this corresponds to the log rho over rho sub 0. So you can express the rho is gonna be rho sub 0 exponential minus g squares over 2h squares. H is expressed c over omega sub k. We call that this is scale height. Then graph is given density distribution in the z coordinate. Density becomes the maximum at the midpoints of the z equals 0. And the density is decreasing, and then approach to the 0 at the z equal infinities. Then we'd like to estimate the ratio of the scale height over the distance from a protostars. H is expressed c over omega sub k. So r omega sub k is expressed v sub Keplerian velocities. The thin disk approximations indicate the sound speed is much slower than the Keplerian velocities. So in the accretion disk, sound speed is much slower than the Kepler velocities. Then we'd like to consider the equation motion in the r coordinate. So this is the equation motion in the cylindrical coordinate. The v sub z equals 0, and the v sub theta is much larger than the radial velocity of the v sub r. Then equation becomes simplified. Then we'd like to estimate of the each terms. First term in the right hand side, p is a rho c squares. Then c is going to be cancelled out, and the c square over r. And the gm sub star over this term is expressed v sub Kepler square over r. Actually, this term is much smaller than 1. So the first term is much smaller than the second terms of the gm sub star over r squares. We can ignore the first term in the right hand side. Then v sub theta is expressed the square root gm sub star over r. This is a Keplerian velocities. So we call such a disk is a Keplerian disk. The rotational velocity of a gas particle follow the Kepler velocity of the square root gm sub star over r. The angular velocity can be calculated v sub theta over r. So square root gm sub star over r cubes. So if you consider the large radius, small angular velocities, if you consider close to the protostars, large angular velocities. Keplerian disk possesses a shear stress due to different angular velocities. The equation of motion in the theta coordinate. This is the last equation that we use. The last term is added to explain the viscous terms due to the shear stress. So we again use two assumptions. Round theta is equal to 0 is an axisymmetric assumption. And also v sub z equals 0. The equation is simplified, and the v sub theta is a constant value Keplerian speed. First term is 0, and also this term is 0 because of this assumption. And the v sub g equals 0, so this is 0. Then second term and the final term is combined into the single terms. Right hand side, first term is 0 because of axisymmetric assumptions. And the last term is expressed using the kinematic viscosity of nu. Then it's gonna be this. Then we could integrate over the vertical direction on the g directions. Then rho is converted to the sigmas because of v sub theta equal r omega. Then you can substitute this v sub theta into this equation. Then divided by this term is gonna be sigma r v sub r is expressed with the r, sigma, nu, and omegas. This is the equation of the continuities. If you solve the equation of motion in the r direction, you will have a Keplerian velocities. And the equation of motion in the theta direction, circular direction, as I show you in the last slide, sigma r v sub r is expressed in this equation. Sigma r v sub r appears in the equation of continuities. Then you can substitute these terms here. Then you will get this equation. We have already know the omega as a function of r. Then you can substitute. This omega is here to calculate. Then we have a basic equations to describe the evolution of the surface density of a accretion disk. Okay, this is the end of this lecture.